Let's go through Liquid 851, loud and rich. So it gives us two array. One is richer, and this is two-dimensional array. For every element, there are two. That is the array that has two elements. The element, for example, 1, 0 means the index, the person 1 is richer than the person 0. So it has a rich relationships for the first index. And the second one is a quiet array. Means um, the person, for example, the person 0 has a quietness factor to be 3. So we want to check, for example, the person 0. For person 0, the person who is richer than him, what is the loudest person, the index? For example, this is person 1, right? Person 1, the person richer to him is person 5, and he is loudest among all of the people richer than him. We need to return this kind of integer array. So the loud is this quietness means we need this have the quiet number to be small, right? So we know there is a rich relationship. So we'll see 1 is greater than 0, right? And 2 is greater than 1, right? So, and also 3 is greater than 1. And 3 is greater than 7. 4 is greater than 3, right? And 5 is greater than 3, is richer than 3. And also 6 is richer than 3, right? So the things that for example, if we know what's it that the shape is like this, right? If we know, for example, the richest person, the person we can do some kind of what's it 3 is richer than 1, right? And 2 is richer than 1. So um so that means the 1 we need to have some kind of mechanism to traverse to 1, right? Um, to traverse to 1. So we know, for example, if we find the loudest person among one's parents, right? And the loudest person, um, for example, in this kind of part is 2, and possibly the loudest person in this part is 5, right? So we know all of the one's parents, like the upside part is richer than 1, right? So we know we just need to compare what is the loudest person among 2 and 5, right? So we'll find 5 is the loudest, so we can get this one to be 1's loudest person, right? So we just need to compare those 1's upstreams to see because those are the person who is richer than 1, right? So if 3, we already calculate the one which is the loudest, and also 2, this part, this stop tree, we already calculate who is the loudest. We just compare everyone, every upstreams, right? So we can safely to say the loudest of this kind of subtree 3, and also the loudest, those we find the most loudest one, right? And what can be the loudest of 1, right? Um, so if we draw these countries, we can think about two approaches. One is the topological sorting. So for the topological sorting is that we traverse from integers with to be zeros, right? To next its child. So we know every child will not be richer than its parents. So that means if we goes to its child, the parents loudest can be a candidate of child's loudest, right? Of course, the loudest we should also compare the child itself. So that is the topological sorting approach concept. And also we can do uh, DFS and memo, right? So the thing is that if we do DFS and memo, we have a result set, right? So we DFS this tree, find the loudest, and also DFS this tree, find the loudest, right? So we can compare to be what is our once loudest. So I'm going to write two approaches. One is using topological sorting, another is using DFS and memo. So let's begin to write code for this. So first one we want to do is to do the topological sorting approach. So we are going to let have int n equals height dot length, and we need a result, right? New int n. So what we do is for we can have do this for we know them every person have a result, right? So we know the result I will be at least I, right? So we can set the initial value smaller than n I plus plus. We can have the initial value result I equals I, right? Then let's compose the graph. We can use this kind of array equals new list n. So we are going to we can have arrays set all graph a goes to new array list. And we can have a integrate, right? Plus new int. Okay. Yeah. So we compose the graph. Richer. So we are going to have a graph. So we know topological sorting is that we from the richest is integrate 0, right? So that means if we go to a child, so the person who is richer will be graph's parents, right? So our map key, the richer will be the map key, and the value will go to the person who is not richer. Then there is some relation less richer than current one, right? So we are going to have richer 0 add rich 1, right? So also we need have in degrees richer 1. So we are write q integer q equals new array type. And we are write for int I equals to 0, I smaller than n, I plus plus. So we check integrate. If integrate I equals 0, right? So we are going to include offer I. Then what we do is that we are just while Q is not empty. So we're going to have int current equals Q dot pull. So we're going to have int next. Next will be less richer than current one, right? Graph current. So we'll write if add result next, right? So initially we set this result to next to be itself, right? So if this one is is quieter, right? Then result current. That means uh current one is louder, right? So so that means we can have result next equals result current, right? Because current one is louder than next. And also we know because for this kind of relationship, the current one will always be richer than next, right? Because for every child, it will be uh, less richer than its parents if there is a child relationship, right? So doing like this, we can safely get a current one. If it is louder, we can set this one to its child. So also we are going to have in degrees next should decrease by one, right? So we'll write if in degrees next equals 0, we're able to enqueue the offer next, right? So in the end, just a return result. So this is a topological sorting. The topological sorting is that it guarantees that the parents will always be richer than its child. And also, the parents, the loudest one, can we can safely contribute to its child, right? So because if we have the parents, then we go to its child, we already compare, right? So we can safely find all of its parents' loudest one to its child, and also its parents. If there is a parent and child relationship, that means the parent is of course richer than its child. So for this kind of approach, we'll see there is we use a queue. So this queue we'll say um, uh, every every person is going to in queue once. Um, so it will be linear, right? And also we are going to compose those kind of um, results and a graph. And for this composed graph, it will be O M, right? Depend on how many richer this the size of richer, right? So this will be O M. This is O N. So it will be O M plus N, right? Space will be also M plus N. Um, let's write topological sorting in Python. So we are going to have n equals length of quite, and so we are going to have a result and graph in degrees equals result will be list of range and graph will be, let's have this one for underscore in range and integrate will be this one multiply n. So let's compose the graph in richer. We're going to have a graph R0 should append R1, right? So this graph that it's coming from the richer to less richer, and in degrees R1 should plus equal to 1, right? And then what we do is we need a Q equals D deck I for I in range n if in degree I equals 0, right? Then we'll have while Q is not empty. Current equals Q dot pop left. And for neighbor in graph current. So as if part result neighbor is greater than part result current, right? Means result current is louder. So we can safely update result neighbor to be result current, right? So we'll also have in degrees neighbor should decrease by 1, right? So we'll say if in degrees neighbor equals to 0, then we're going to enqueue, right? Append neighbor. So in the end, it just return result. And we'll say this first approach, we can use topological sorting. The concept is that when we coming from the parent to its child, we can make sure the parents will always be richer than the child. So we just find the largest one among its parents, right? So but this question, this can give us another concept about a DFS or post-order traversal, right? So the things that if we have a richer part, which is the child tree, already get the richest among, for example, among this tree, and also richest among this tree, then for our parents, we just for example, the richer we get the loudest among this tree, and the this tree among all of the trees, right? The child trees, we know the loudest. We are going to compare. Also, of course, we need to compare itself or get the loudest of this parent tree, right? So that we can update um, the results, right? And And for this one, the thing is that it's not just a tree, right? Because it is possible some of that will be um, calculated more than once, right? So in that case, we can save some of our result to a memo array. If it is a tree, post we can just use the post or traversal, right? But we have a result array, right? But this one is a graph. If we do post or traversal, it is possible some of the result already been calculated. So we need to save that to our result. We can also call this a memo, right? So we can also write this kind of approach. So um, let's have int n equals part data length and int result equals new int n, right? So let's set here this kind of result to be -1 um, because the thing is that we can set this one as I, but the thing is that if we use this result as a memo, we can use -1 means this one hasn't been calculated yet, right? But if we set this as I, we don't know whether this already calculated or not. So let's set this one as -1. So if result I has result, then that means we already calculate that. So we are going to have at least integer graph, right? Equals new list. And also we can have arrays set all graph k goes to new array list. But for this one, we are going is that the parents, this graph, the key will be um, the index of the key, right? Will be the less uh, less richer person well on the top. So we'll see because this post traversal. So the richer one, if we find the loudest, it can pass into its parents. So the parents will be less richer. The child will be richer, right? So this graph is from less richer to richer. This will be because the post order traversal. So the graph is should have the reverse order than topological sorting, right? Topological sorting is that we do this and then goes to its it, then goes to the less richer one, right? So the thing is that we just need to make sure we are always calculate the one which is richer first, and then goes to the person who is less richer. So in this kind of scenario, we should have the key to be less richer one, and the values will be the child will be richer one, right? So when we compose this graph, we need to make sure the order is also reversed. So we're going to have a graph richer one should add reaches 0, right? So then what we do is that for int I equals to 0, I smaller than n, I plus plus, right? So we just DFS graph. We can also here if if result I doesn't equal to -1, right? Otherwise, we can DFS graph I height result. Then in the end, just return result, right? So this result is like a memo. So private int DFS list of integer graph into current, into fight, into result. So we check if it has already have a result or not. If result current then equal to -1, right? Means it's already been calculated. Just return result current. So what that we'll know the result what at least to be current, right? So that's using a mean. Because we find the minimum of the quantities, right? So mean equals current. Then what we do is set for int next in graph current. So we'll have we're going to have int answers equals DFS graph next five result, right? So we'll say if five answers is smaller than five mean, right? Then we're going to have the mean equals answers. So we need to step this kind of result current equals mean and return mean, right? Let's look at it is should if it equals -1, right? Then we need to DFS. If so, let's say this is quite fast, and we'll say the DFS and memo the uh for every person we are going to 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 we'll say what is the time complexity every person is going to DFS once. And also for this person, we are going to traverse the graph as its relationship, right? So we'll see the DFS depth will be OM plus N. And also this kind of graph is ON, right? And for this kind of graph, the size is also dependent by its the richer relationship. So we'll see the space will also OM plus N. This also this one is we have an OM, right? OM time complexity as well. So the time and space, the two approaches, they both have OM plus N time complexity and OM plus N space complexity, right? Let's write this in Python code as well. So we are going to have N equals the length of height, and we have graph result. Graph will be for in range, and right. So we're going to have result instead of set of I, right? We are going to set as -1 right now, so that we know whether it's already been calculated or not. So for U V in richer, right? Just graph V append U, right? So we are this will be less richer, then goes to the richer one, right? Because DFS is post, that means that we traverse richer person first, right? Then we are going to have a DFS. We're going to have current as int. It goes to int, right? If result current done equal to -1, that's a return result current, right? And we're going to have mean person equals current, and for neighbor in graph current. So we'll have answers equals DFS neighbor. So if we quiet mean person is greater than quiet answers, right? Then we'll have mean person equals answers, right? And also we need to save this result. So result current will be mean person, and the return mean person, right? So for our main function, what we do is that for I in range n, right? So if result I equals -1, right? Then we'll have DFS I. Then in the end, just return result